It's quite a pleasure to be here where I get to reconnect with old colleagues like Scott and Steven, as well as enjoy a slightly improved temperature than I'm accustomed to this time of year up in Seattle. As Jim also hinted, it's a bit of a, if I had to have a subtitle, it seems like this entire series is a bit of a family affair. So I'll try not to be too incestuous in that my advisor is speaking next week. My advisor's advisor, who also ran a group with me at Stanford, Pat, already spoke. I'll try and build on his talk a bit. And then my student, Mike Bostock, who created D3, will be speaking shortly after that. And so while I'm probably best known for visualization, as Jim has shared with you, I thought I'd use this talk as an opportunity to touch on something else, basically a theme that's a bit higher level, but it's run through a lot of our projects, both in visualization and in other areas of data analysis. And to a really rough, first approximation, one of the observations that motivates this, is the idea that, my software, by and large, often doesn't know what I'm trying to do. It may be the result of human-computer interaction researchers, a user design team that might have a very good sense of task and then distill that, or even in a sense compile that down into the workings of software. But in a way where humans might have a great semantic idea of what their users are trying to accomplish, the software might not have anywhere near a correspondingly rich a model. And so one of the probing questions here, a bit naive at first, but hopefully we'll flush it out as we go, is well, what if software did? And as I raise this, you'll be forgiven if maybe your first instinct is to cringe, particularly if you lived through regimes like this, where you have intelligence assistants who annoyingly note that you're trying to write a letter, pop up and interrupt you in the middle of the task in ways that may be inappropriate. And I'll sideline a much longer discussion of Clippy. There's a whole bunch of interesting history here, including the fact that the original models from Microsoft research teams were not what shipped, and whether or not anthropomorphization of support is really the right approach to take. So there's a bunch to unpack there. You'll forgive me if I skip by it and say that what motivates me is actually starting with much more modest beginnings. So things like this, if I have a text editor and I'm in contexts where maybe spelling or correct grammar are important, maybe with just a small minimal model of things that are valid and useful for the task of writing, maybe there's some automated support that might predict edits that I would make, in this case, changing a spelling error. Moving on to a slightly more complex example, maybe sort of a useful microcosm of some of the things that I care about, would be things like this, so autocomplete. So here I'm writing, a query to Google. I write an NFL. Not only does it immediately provide me results, including structured data as well as search results, it suggests possible refinements or extensions of my query. So in this case, it uses the context of the interaction, in this case what I've typed, as well as data on past activity to make a set of predictions that should hopefully accelerate or improve my activity. And this can be useful in different contexts. If I search for San Diego, I might be able to jump a couple steps in my work if I care about acceptance rate, tuition, or medical center, which apparently are things that people search for regularly. So acceleration might be one goal. But I think something interesting to think about, too, is how these ways actually support ambiguous user intents. So for example, if I want to learn more about Scott Clemmer because I've heard great things about his HCI research, this might suggest to me that I might also be interested in his work in MOOCs or perhaps his marital status in this case, which you'll have to ask Google what's going on there. But nonetheless, the idea that these can play multiple roles. It might help our task, but might also allow us to go down paths that we didn't previously consider. And so if I was to say, look at this at a more schematic level, so let's think about something like search query autocomplete. I start by typing into a text box. And as I type, in good user interface design, I immediately get a response. So obviously, the letters that I type appear on the screen. I can see that the system's responding to me. But simultaneously, that's using as input or evidence for searching over a space of possible suggestions, making predictions, one which I might then pick. Or I could choose to type something else. I could delete or move forward. And so I have this iterative loop as well. So the system is really acting as a collaborator in this process of expressing a search intent. And so we'll look at this pattern in more detail later. But you'll notice there's two really interesting actions here from the perspective of the system trying to make the prediction. That initial input is providing guidance. So it's providing context that limits the scope that the system's going to search over. So in this case, I'm actually steering the recommendations I'm going to get. And then I get back a set of options at which the user then also has to make a decision, whether that's to select an option or to say, no, you're on the wrong track and refine it some other way. So for the purposes of this talk, we'll refer to this as the guide-decide loop. And we'll look at how this might apply in other contexts. So what makes this a relatively simplistic microcosm, despite a lot of interesting statistics behind this application, is that the input and output domains are the same. So we're using text to express text. And so this actually has a lot of features that simplify the interaction. So one of the questions that we'll explore in this talk is, what about more complex input-output relations? And how can we take some of the useful things of this model and apply it in more complicated situations? So here's some of the objectives of the types of interfaces we'd like to build. We want to accelerate successful tasks like we typically do. We also, particularly with data, want to scale to large data or tasks that might require lots of repetition. So that's a different goal than what we might see with a search query. As I mentioned earlier, support discovery and support perhaps ambiguous user intents. If I come to a system with a vague notion of what I want to accomplish, does the system actually help me refine that in useful ways? And similar to autocomplete, can the system get smarter over time? Can it learn from usage? And so the strategy that we'll explore for achieving this is to actually create a model of user interface actions. So even if the model is simplistic but useful, this can be very valuable. Can the system reason about the steps I might take and use that as a means to provide predictions? We'll also see by doing this as a domain-specific language, really taking a language model to expressing the user task, this also provides some other benefits where we can decouple how the user interface reasons about the task and provides assistance from actually then running the resulting generated programs to do things like scale to large data. And I'll do this in the context of two examples. The first should be familiar from Pat Hanrahan's earlier talk. We'll briefly walk through some design ideas in Tableau that influence our work. And then I'll share the results on projects we've done on cleaning and preparing data, starting with research projects at Stanford that have then gone on to become the basis of Trifecta, a startup company I helped co-found based in San Francisco. But before we dive in, I just want to set the larger scene. These are some of the things to look for across the examples. Why this approach to modeling user tasks in domain-specific languages? So we're going to model the task as a program. And that might sound complicated. In some cases it is. But oftentimes the program is just a sequence of actions. We want to understand what those actions are and how they compose to be able to perform more complex tasks. This model then provides a formalism for reasoning about actions. So for example, we might enumerate possible statements in a language, rank them, etc., and use this as a way to provide predictive suggestions of where people might go. This also provides a natural structure for learning from usage. So I might learn something about likely sequences of actions in a language. I might also learn other types of statistical patterns. For example, in a ranking function, I might have lots of different metrics, and I want to know how to combine them. I could fine-tune those weights over time. So there's various ways that this language model actually can learn and update its weights based into response to what users actually do. And by modeling this as a program, we can reapply it to new inputs. So we get used to repeat, perhaps repetitive tasks. We can also then take this language and basically approach it as a standard computer science problem, compile it to various areas. So I might have a program I generate in my UI that then can run at scale across a cluster. And in fact, that's an example we'll see. So just look for these points because this is some of the motivating reasons for why we'll see these sort of language-infused user interfaces. So with that preamble, let's jump into the first example, which comes from the domain of data visualization. And so I'll trust that the majority of you are familiar with this interface, which is Tableau, which is a data visualization tool, particularly well designed for exploratory data analysis. So on the left, we have a view of our data table, so different variables, and subdivided into whether they're discrete or continuous. And then you can drag them out into these visual encoding shelves. So I can map data variables to properties like X, Y, color, shape, size, and then generate visualizations very rapidly, hopefully gaining insight into the data set. So for example, here's an initial build out where I might be a company. I have some different categories. I have different regions. And I'm looking at my sales volume in each one of those regions. So in this case, I have two ordinal or discrete variables and one continuous output, in this case, the sales. And I can build this up further, in this case, via drag and drop actions. So if I wanted to also subdivide by customer segment, I can drag that out, drop it on this shelf, and now I've further subdivided my data table. I might also want to compare sales and profits. There's various ways I can do that. One simple one is drag out profits here, put it next to sales, and now I get side-by-side bar charts, so I get some comparison. So you can see I can very rapidly build up these visualizations. And what's interesting here is there's actually a fully formed formal language working behind the scenes here. So if I zoom in on the schema here I've basically taken a bunch of nouns, these different data variables, and just dropped them on shelves. And what Tableau is actually doing behind the scenes is inferring verbs between those nouns. So it's actually doing what's called a cross product between category and then the quantitative variable sales. And that sales has actually been concatenated, so they're spatially contiguous here, sales and profit together. Meanwhile, there's what's called a nesting operator between region and segment doing this drill down. What's interesting here is actually then doing inference into a formal language, basically an algebra for specifying a table, and then this gets translated into different representations. So for example, given this specification, not only do I have all the information I need to build out this visual view, I'm also using it to automatically generate queries that I can run against a database. So for example, from here I can infer a clause that's going to be grouped by category, region, and segment when I'm computing the sum of sales and profit. So again, the basic idea here is that I actually, underneath the scene, have what Tableau calls VizQL, which is a domain-specific language for tabular visualization. And so here we have a small set of operators, which are each applied within these encoding shelves, and a small set of parameters or operands, basically whether it's a discrete or continuous type. And what's interesting about this is that, one, it can be compiled to these different representations. It simultaneously describes database queries and visualizations. But it also does so in a way that you're visually making linguistic statements in this underlying language. So when you're drag and drop, you're moving around these nouns. And in this case, the UI actually infers the verbs that then turn that into an actual, honest-to-goodness language statement. And so if we look at this schematically, you can say, well, we start with this base representation, which is we have this underlying language for visual encoding and query specification. So that given a data set, we can apply this VizQL query and result in a set of query results and correspondent visualizations. But of course, what the user experiences is up on this plane. So they see a view of the database table, they do drag and drop to these shelves, and that produces the visualization. And so what we have is actually a mapping between two different languages. One's more of a formal textual language, more akin to programming, and the other is the visual language of these drag and drop shelves. And so we use notions from category theory, which is that we take about one domain, we translate it into another domain, which is formally referred to as a lift. And then at the end, of course, we can take that visual specification and then ground it or compile it back into the underlying language. And this is a trick that actually works well for a surprising variety of applications, particularly ones dealing with data. But a number of design decisions and issues also come up. So one is the question of expressivity. So in this case, what we're saying is a domain-specific language program is the composition of lifting to the visual domain, getting the results of some set of interactions, and then grounding it back into the actual language domain. And so we can ask, well, do we actually have a one-to-one mapping between these two planes? In other words, are the languages isomorphic? That is, can everything I express in one language be expressed in the other? And it turns out in the case of Tableau, the answer is no, you can't. So for example, there's sometimes instead of nesting, I might want to take the cross product of two discrete or ordinal fields, or I might want to concatenate two together, both of which actually create legal visualizations in the underlying language. But the Tableau UI won't let you express them. And that's fine because they made the decision that the ease of use of the visualization was worth this trade-off in the expressive power of the tool. So some design issues come up that even if you have this useful mapping between languages, the mapping may be imperfect, and then there become things that sometimes may be useful, but you simply can't express. There's also the issue that you notice that while we have this mapping between languages, we're missing some of that predictive power that we saw in the initial example involving autocomplete. So one of the things that we'll look at is how do we augment this particular model to get the benefits of both of these approaches. So Tableau is one exemplar of this sort of like language mapping-based tool. There are many other interesting ones in the literature. So there's tools for network visualization that follow a very similar approach. And even in my own lab, we built a tool called Lyra, which was done by my student Arvind Sachinarayan, which is basically saying, how can we build something akin to Adobe Illustrator, but for data graphic design? And underneath this visual tool is actually Vega, which is a high-level declarative language for data visualization. And so while people do drag and drop and configuration in a visual tool, this is actually all being translated down to an underlying language, which then allows the visualizations that are produced to be reused with new data or published independently on the web. So just by itself, this language mapping technique oftentimes allows us to create reusable, oftentimes scalable results of interaction, but one that can be specified in a graphic, often direct manipulation way. But for now, let's move on and look at a more complex example, which is in the area of what I call data wrangling, which is basically all the work you have to do with data to make it useful for tasks of visualization and analysis. So this can be reformatting, this can be cleaning up data, this can be joining multiple data sets together. And so this is one source of inspiration for us. Back in 2012, we ran a study of over 36 analysts and companies, and we got back lots of quotes like this. I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. And some of you are nodding your heads in the room. Perhaps you've experienced this pain firsthand. What's funny enough is we go around and show these quotes to people, they really take issue with it. Not that they disagree with it, they're like, no, that 50% estimate is way too low. And so, you see this now codified. At the time we were trying to, make this well known. Now it's talked about a lot in the field, and you see all the way that, it's like it used to be the elephant in the room of data science work. It was like where all our effort went, and we weren't talking about it. So now I think it's become a more front and central concern, where you see things like Big Data Borat telling us that in data science, 80% of time spent prepare data, 20% of time spent complaining about need to prepare data. Right? And this 80% actually comes out of books on data warehousing. We've talked to folks like DJ Patil and Jeff Hammerbacher who run data science groups. It's like, yeah, this is like a big problem in terms of human productivity. So what can we do? Well, even relatively clean data exhibits this problem. So here's your tax dollars at work if you're here in the US paying taxes. This is from the Bureau of Justice Statistics. So it's various stats about housing crime across different years and different states. You can load this into Excel, no problem, but obviously this format is not really well chosen for loading it into R or a database or a visualization tool like Tableau. So even this relatively clean data can often have severe formatting issues. And so recognizing this problem and having experienced it firsthand, a number of us, led by my former PhD student, Sean Candle, looked at different ways that we can turn what is normally a coding process, so writing one-off scripts to transform data into usable outputs, into something that can be much more visual and interactive. And one of our first projects in this line of work was a tool called Data Wrangler. So let me just go ahead and jump into a demo for that. So here we see the same housing crime data as before. In this case, a familiar data table layout. And then you also see a history on the left. You can see that we've already split the data into rows and columns. And you see there's a number of different commands along the top. So these are actually the verbs of a language for transforming data. And I could actually drill down and look at the different parameters that some of these operators can take. So this would be more similar to a menu or dialogue-driven system. But the primary interaction paradigm we were exploring here was let people indicate their interest in particular elements of the data and have the system perform some kind of higher level autocomplete. So in this case, I might click row 2. And a simple inference might be, well, what can I do with a row selection? Well, I could delete it. But I also can look at the content of that row, and I see that it's empty. So the second suggestion on the left here is to delete all empty rows. And you notice that as I do that, I highlight in red all of the rows that will be deleted. So without even reading the comment, I can get a sense of what will actually happen if I execute this transform. So I hit enter, and then the table updates accordingly. My transform's added to the history. And then I can continue on in this process. I see that metadata, the column headers, are buried in the text here. So I can go ahead and promote that to a header. I still have other rows that are lingering with that metadata information, and I can delete them just by matching the values of those entire rows. Now the trickiest bit is actually pulling out those state names and associating them with the rest of the data. So I can start by indicating my intent by selecting the text Alabama. The system correctly guesses that I'm doing an extraction, but purposely makes some very simple inferences at first. So looking at things like position in the string or doing exact content matching. But I don't even have to read anything on the left to see that the matches don't line up. Alaska is not highlighted, Arkansas is being cut off, etc. So I can go ahead and just refine my input by giving an additional example. And you see that now the output here in the preview looks right. If I read the language on the left, it's actually learned an extraction procedure to take out the text that occurs after the word in. So that's great. So now I can create this new column. It has the beginnings of the state names. And as I'm doing this, you probably notice some other things. For example, I've inferred that this is largely numeric data. And this green bar here is showing me the percentage of things that parse as numbers. And then in red, I see the percentage of things that don't, which are these reported crime in rows. Similarly here, I see this is a text field, and it has a large number of missing values indicated by gray. And I can just click the column to get suggestions on column level operations, which can include interpolation through missing values, which in the case of categorical data would just be filling up or filling down. So here I can fill in that data. So now I'm actually filling in those records in a useful way. And all that really remains to be done is to get rid of the rows I no longer need. Now, while I could throw away things that don't parse as numbers, that might be brittle. If any of you have worked with spreadsheet data, you may have seen things like entries that say 2004A, where A is a footnote to the end of the spreadsheet. So let's not jump ahead of ourselves, and instead more carefully craft a transform where we get rid of the rows that start with reported crime in. And based on this selection, the initial guess of Wrangler is that we're doing an extraction procedure, and that's incorrect. So in this case, we can give corrective feedback in the form of the type of operation we want to perform. So if I indicate my interest in deletion operations, it can update its guess. In this case, it now suggests a deletion with the appropriate query predicate. So I can go ahead and do that, and now I actually have a very nice relational table that I could load into another tool. I'll spare you the minor detail of renaming the extract column here. But in addition, I have all of this history here on the left. So if I wanted to, I'm now ready to export the data. And for data that's relatively small and fits in this web-based tool, I can go ahead and just take that output, whether it's a CSV or JavaScript object notation or any other of a number of common formats. But the script on the left here is really just this pseudo-natural language rendering of statements in our own DSL, so a domain-specific language for data cleaning. And so I can take that language and then cross-compile it. So instead, I can generate the Python script that performs all of these cleaning operations. And in a way that I could do this at a larger scale than I could in the browser alone. We actually generate JavaScript, which is what's running directly in the browser. In this version, we also generated queries that could run in a relational database. So the idea is here, not only can we use this language as a way to provide predictions, we can use it to scale up and actually run the transforms that we trained on a sample here over much larger data sets. So that's what we did in Wrangle. So that was Data Wrangler. We then went on after a series of projects looking at other forms of data cleaning and quality assessment to found a company. So it's called Trifecta, and the tri here is actually sort of what we call the trifecta, the analytic trifecta of data, people, and computation. It's also no accident that we happen to have 3 co-founders, myself, Sean Kandel, and also our collaborator from Berkeley, Joe Hellerstein. And so we've built a lot on Wrangler, and I'll show you a quick demo of some of what we're doing in Trifecta currently. A number of elements are pretty familiar. So for example, we have a table display. In this case, we're looking at data from the US Elections Database, Federal Election Committee. And so we see all the different political candidates. And if I wanted to do things like separate out last names from first names, for example, just as before, I can make selections. It will give me previews. In this case, we moved away from a reliance on language initially to actually showing very specialized previews that allow people to browse through the number of suggestions down here. In this case, I can see the results of this different extract procedure, both schematically and then on the actual data itself. But one of the other things we explored here was creating additional representations of the content. So rather than just showing a table, we're actually automatically generating visualizations. So you see these histograms along the top of each column. In this case, we have an ID field, and we see that the most populous values only occur once. So that's great for a database key. You don't want it to occur more than once. But I do see immediately that certain candidates occur more than once. And some occur 3 times, some occur twice, so that could be odd. And so I can immediately get some corrective insight in ways that my data quality may be off. And so I can also use these visualizations as springboards for corrective transformations. I can also scroll this in this way. And if I want even more details, I can pull those up. In this case, I actually created a statistical profile of the data. So I see all the valid things that don't parse. I get various descriptive statistics. I see the top values with more detail. And I also see a histogram. And because this is a text field, what we histogram is actually the length of the strings. And it turns out in this case, this actually gives us a very useful cue to data quality in that if you have names that are way too short or way too long, they actually show up as outliers. And in fact, I can actually select the outlier line here to use the visualization as input to trigger additional types of recommendations. So in this case, I could either filter or keep just the outliers. And because they're just too fun to resist, I will keep them. And then go back to the table so you can get a sense of what, the names of some of the people who are ostensibly running for office. So some of my favorites include His Royal Majesty Caesar St. Augustine de Bonaparte. So apparently amalgam of historical figures. I'm terrified that Satan, Lord of the Underworld, His Majesty Prince of Darkness is running. Some of you may have already known that. I didn't. The Prophet Earl, whoever that happens to be. Various variants of Harry Potter. And also Remo the mini schnauzer, the cutest dog ever. So these are people actually registered with the Federal Elections Commission. And so one could have a probably whimsical data science analysis just figuring out what, if any, influence or fundraising are these types of candidates doing. And I can, of course, back up and then explore other things. So for example, I might look at things like the year. And then here, outliers are interesting. I have candidates who are listed for races in the year 2052. That's a little odd. And I might look at other things like, what state are the people hailing from? In this case, because we know something about the semantics of the state, we can actually automatically generate appropriate visualizations. So for string data, that was string length histograms. For numeric data, that's numeric histograms. For other things, we can also do geographic representations. The idea is to not spend time configuring a view, but rather get a view that's useful for that type of data that is then immediately actionable. So if I only wanted to look at Texas candidates, it would be very easy for me to then trigger a transformation to do that. And so I can go on in this way and perform a number of transformations, including things like if I wanted to window it down to people who are just running for president, I can add that. And as I do this, you might notice that there's a lot of other highlighting going on. I might say I want things that are only running for office in the current election cycle. And you see as I click these things, not only do I get suggestions, I see how that data distributes across all of the other variables in my data table. So now, for example, I've winnowed it down. If I wanted to export a data set that focuses on the current crop of presidential candidates, I can do that. So again, going beyond Data Wrangler to include visualization as a first-class content representation for exploring the data. I could spend a lot more time here, but in the interest of time, I will jump back into the slides. So you saw some of the things that we've explored with Wrangler and Trifecta. And what we're approaching here was really trying to change the traditional way people did data cleaning, which is, if your data was large, you would maybe have to sample it, but you'd start by writing a script. So with the exception of the people who spend hours in Excel, the other most common way is to write code, whether that's in Perl, Python, R, et cetera, to do that cleanup. When the data is large, you actually had to pull a sample out for testing. And then you would run your code, see what errors resulted, fix them if they were obvious, and otherwise then profile the data. So for example, visualize it to see, am I getting the outputs that I expect? And so what we're trying to do here is change the interaction paradigms to really switch these two planes. So instead, you start with a content representation, whether that's a table or a histogram or other visual representation that directly provides affordances for interaction. And then those actions, those selections, then serve as input that then can be used as a hint or guidance to a search algorithm using machine learning techniques to then actually predict a distribution over possible underlying language statements. And then from that, we then get a ranked list of these suggestions. And the primary way of interacting with them is, sure, I could read this language, but we found in user studies and in deployments that people are much more effective, faster, and happier when we provide useful previews. So really discriminating between these different transforms based on a visualization of what their consequences would be. And so in that way, really trying to make a much more visual and interactive experience for this otherwise tedious task of programming data transformations. And we call this overall approach predictive interaction. So behind the scenes, what we're doing is actually, as I mentioned, doing search over a data transformation language. So we have a bunch of different verbs. So that's like split a column into multiple columns, extract text from a column, filter, derive new values with a formula, up to more structural things like pivoting, creating aggregations, and also joining and unioning with external tables. And we try to keep a very small number of these transforms. So what's the right set of operations that actually have a nice expressive space that we can actually implement all the different types of transformations people need? The other thing we do is that each one of these transforms might take multiple parameters, but we actually have a very small fixed set of parameter types. So things like row selections, column selections, text selections. And I'd like to take a moment to spend a little more time on text selection because it's a useful microcosm for understanding how the rest of the tool works. This is actually a design pattern where you can take some of these language-based tools and nest them within each other. So our whole way of inferring text selections actually deals with a language within the larger Wrangle language shown here. So consider this example. In this case, is actual data taken from people doing an online advertising campaign. So there's a number of different parameters here that determine what shows up in the ad. So is it dynamic? Is it mobile? What's the screen size, et cetera? And say I want to parse this out. So I select some of this text. So like dynamic might be an example, mobile might be an example. And I can see a preview here, which looks like it's doing the right thing. But maybe I want to verify that and understand, well, what's the actual language statement that's producing this preview? And in an initial prototype, we searched over the space of regular expressions, which is a very common formal language for doing text extraction. And as you can see, it's extremely usable. So what does that do, right? So let's just zoom in on that. What the heck is going on here? So let's even break down, what am I even saying with this sort of gobbledygook of symbols? Well, it turns out, with these special directives, one is a look behind and the other is look ahead. So I'm saying match the stuff that occurs between these two so long as it's not an ampersand. So basically, after you see this, take everything until you hit an ampersand. That's what it's saying. Now, it's actually much easier for me to just say that to you than for you to decode this, let alone all of the other issues that are regular expressions raise. So for example, some of these are control characters. Some of these are actually literal characters, like I actually mean an ampersand here. And regular expressions are horribly inconsistent in that some special characters like digits have escapes, whereas other characters where you want just the actual character is escaped. So it's kind of a syntactic nightmare. And as a result, I think this is probably the best example that I've ever seen of a language that fits the mantra, write once and read never. right? So the system will interpret it, and that's great, you know, and it can efficiently process text. But even revisiting your own code with a complex regular expression is really nasty. And so one of the insights we had here was like, A, if we want the language statements to be understandable by people, we're going to have to design a new language. We want to actually have it compiled down to regular expressions so that we can run it in basically any system ever. Like, we don't have to write a runtime for everywhere. So the fact that we can write a language that also maps to regular expressions is very useful. Turns out it also is very helpful for writing better predictive algorithms. So we actually tried to map this into a different kind of language. So one based on these certain types of selection prepositions. So what this is saying, and this is like our resulting language, select the text that occurs after this string, add tam source equals, but before the ampersand. So basically just a syntactic distillation of my earlier description. And what's interesting about this is that we can have a bunch of different clauses. So after, before, but also at the beginning or the end of the selection region, or exact matches to the selection region. And so this is what we actually see, you know, if you look at the underlying language statements generated by Trifecta. And the way that's done is we actually search and individually populate these different prepositions. So match exactly on this. From to is the beginning, end of the selection region, and after, before. And while this doesn't map to the entirety of what one can do with regular expressions, it covers all the tasks that we've found necessary for everyday data cleaning. And so how we actually arrive at these suggestions is through an inference procedure that goes at a high level like this. The user selects text, and these serve as either positive or negative examples. Based on the positive examples, we process them. So we'll cut it up into tokens, like we'll separate numbers from basic text. We'll include exact matches, but we'll also generalize things. If we see 5 numbers, we'll include a match for those exact numbers, but also generalize it to a 5-digit string, and then even to an arbitrary length digit string. So we'll come up with a bunch of generalizations. And then we'll assign them to the appropriate prepositions here. So we'll generate individually on clauses, from clauses, to clauses, after clauses, before clauses, and then we mix them all up. And so that might sound like a combinatorial explosion, and if you do this too far, it is. But if you actually tune it right, you can limit it to about hundreds of hypotheses, which is enough that in like a millisecond or less, you can run all those hypotheses over the entirety of your sample and get back some data about how they're performing. And so that's where we combine the clauses, we match ons or from, afters, befores, et cetera, and then we just test them all. And so we do that. We actually run them across the data and then use a set of ranking values in terms of determining which are the best. And while that's patent pending, so I can't share you the details, plus you probably don't want to hear it in excruciating detail, I can give you some intuition for some of the things that we do, which is I basically just stared at examples and asked myself, how can I be so good at just looking at output and knowing which selection is the right one? What are the sort of perceptual patterns that I'm leveraging, and can I encode those as ranking procedures? And so here's 2 versions. Imagine I selected the word John. Take a look at the different outputs. So you can see here we're selecting all the first names semantically. And over here you can see that I'm catching John wherever it occurs, whether it's a first name or a last name. So by show of hands, how many people think, given no other context whatsoever, would you prefer the example on the left? Raise your hand. OK, and then the example on the right. So no, and a bunch of you abstain. That's OK. It's not a graded quiz. And they use a lot of factors here. So we might semantically look at things like, well, I'm getting first names and last names, so that seems odd. But even just as simple as the fact that here I'm getting a consistent set of hits with consistent spacing at a consistent position relative to the length of the string, you can actually get some very good little simple metrics that become incredibly predictive. And so in this way, it's some of the insight into the ranking procedure. We also do some other things like basic Occam's razor stuff. So which sort of suggestions cover all of the examples but have the simplest set of clauses. So we can do that for internal ranking as well. And that generates this set of parameters for text selection. And the process for larger Wrangler inference is really just kind of inductive from there. So when the user makes a selection in a data table, we generate a set of parameters. So I just showed you how we generate more or less text selections. Column and row selections are very simple, but we can also generalize. So for example, looking if the row is empty, et cetera. And then what we just do is take those parameters that match the user input and then see what are all the transforms that accept parameters of that type. And again, we generate a whole space of transforms and then go in and rank and cluster them based on what they do to the data and some measures of quality. To bootstrap this, we actually came up with some of our own measures, but each of these aspects can also be tuned through usage over time. So we can use statistics as to which transforms are more likely given previous actions. We can also look at things like how do we fine-tune the weights over the different ranking functions. And then, of course, we end by presenting the results, which in this case is done through visualizing previews as well as actually giving you snippets of those actual transforms. So that's the approach. And the interesting question going forward is, we can do questions at the end unless it's relevant to this right here. Okay. Okay, thanks. So the idea here is like this is a point example. So this is more of a speculative part of the talk where I'm wondering, what are the things that we can do to generalize this? So what are the class of applications where this can apply, and what contour might that take? So just to review, we first looked at autocomplete, which had this thing where based on past behavior and current context, I might predict multiple outputs. We looked at this language translation technique where I might define a formal language, but then actually create a visual language that allows people to more easily make expressions in that. And we get some benefits that the output's actually a program, so we can reuse it, scale it, et cetera. And then taking the next step to combine them, we can actually reason about those programs. So with predictive interaction, similar to before, we start with a domain-specific language that's hopefully well-designed for the task it's designed to support. We do a lifting into a visual representation, which might be these different content representations. You can interact with them. You should obviously get immediate responses in terms of what you're selecting and what your interaction's immediately doing. But then that serves as input, again, for searching over a space of possible transformations. In this case, what we do then is actually search in the space of the language itself. So we go back down and basically search over these formal objects and then bring it back to populate a space of previews. And then you can see what those previews are, select one, or you can do revision. And so again, you see that, and at the very end, we then have a program that we can run. So again, we're doing this guide early on where our input is guiding the possible predictions we're getting and a decide loop. And this can also be iterative. If we don't like what we're getting previewed to us, we might have other recourses for either take action ourselves or provide different input to the system. So that's the overall pattern. And so now you can hopefully see better the points I raised at the beginning of the talk. Like, why do we want to do this? We see that domain-specific languages provide one way of modeling a task at hand, whether that's data visualization or data transformation, and allows us to reason at a higher level and make predictions that may both accelerate the process and hopefully also give people ideas of things they might do that they might not have otherwise occurred to them to do. And so we've also seen some of the necessary components for this. So one, of course, is content representations. So how do we take the data or raw material that we want to manipulate and manifest that in a way that people can make sense of it and also provides affordances for this guiding interaction? We obviously need the language model, which is both the design of a language, but also the means for doing search and prediction over that language. So what is it about the statistics of the language or maybe hand-coded heuristics and combinations thereof that allows us to make good recommendations? And then, of course, we have to close the loop in that our content representations should support preview mechanisms, as well as perhaps additional things like actually seeing language statements. So there might be various ways that these predictions are surfaced in the resulting UI. And of course, this raises a number of considerations for language design. So one is expressivity. So obviously, we have to understand the task at hand, and as the language that we're providing support the necessary tasks. So obviously that might involve a lot of task characterization. It might involve both like ethnographic work, embedding in the field. There's a lot of design methods that need to be brought to bear that you understand the task well enough to design for it. Of course, then we have to understand, well, how I come up with this language? There might be various ways I could design it. What is a good fit for the users I'm designing for? So how well does it fit the problem domain? Can I, and how do people understand it? Like, do the nouns and verbs match the kind of entities and concepts that the people who work in that space actually use to think about what they're doing? This is critical. I don't have any magic bullets, but what I can say is that in every project we've taken on with this approach, it's really about co-design of the language and the UI. So we treat the language as a prototype, we start building UIs, and then we learn from usage, and we end up adjusting not just the UI, but oftentimes aspects of the underlying language. But even it turns out, even things as like seemingly trivial to some people as the choice of words is critical. So how do we even name those nouns and verbs, let alone what they are, tends to be a very, very important part of trying to make this work well. We also want a language to have a small surface area. So if possible, we want the set of parameter types, the set of like verbs, et cetera, to be small. And this is for benefits on both sides. It means there's less to search over, so we can often make better recommendations or search a larger space. But ideally, it also means that users can, over time, internalize that language more quickly. And there's also this question of like, well, can you provide a useful ranking right off the bat? So can I provide useful suggestions? And for us, it came to an intimate knowledge of the domain, starting off with thinking hard about the problem, coming up with good heuristics and search criteria, and then using additional interaction over time to fine-tune that, while also collecting a whole corpus of data that if we came up with new ideas, we could always test it and see how well we're doing. One might imagine a different approach, which is actually start with like the more Tableau-like model, where there's no prediction, and over time, you're still learning over that language, and then start adding more advanced predictive capabilities over time. So there might be different approaches to how you arrive at this more predictive capability. One thing that I can say is that we've had tens of thousands of users use the online Wrangler prototype and received all sorts of fun feedback, including people who say, like, had this been around 3 years earlier, it would have shaved 2 years off of my PhD thesis, which is always great to hear. We've also deployed this in large organizations. So some of the customers of Trifecta include PepsiCo, GoPro, Royal Bank of Scotland. And we consistently hear back that this is actually reducing their data prep cycle by an order of magnitude. So things that were taking weeks, they're now doing in an order of days. And so we see this as some useful empirical evidence that our techniques are bearing fruit. So that gives rise to the final set of questions, which is going forward, is predictive interaction or some variant thereof a fruitful area for further exploration? And my sense is, like, even if it doesn't prove to be a panacea to a huge class of problems, it raises a really interesting set of research questions that might pay dividends on their own. So one, of course, is just to further explore the space. What other types of domains and applications might benefit from this approach? And so one that we've been exploring is an early stage exploratory analysis. So visualization is very powerful at various stages of analysis. Tableau is really good when I have a question in mind and I can express it in terms of a set of data variables and I can explore it. But what happens when I encounter a data set for the first time and I don't know what's in it, I don't know what quality problems are there? You saw some of that with Trifecta. We're doing some automatic visualization. And Voyager is really an extension of that approach. So the idea here is I loaded a data set. In this case, it's about a set of movies. And I've done nothing, but it's automatically provided me a set of summaries for each column. So I immediately get some insight into the distribution of values and also maybe some data quality errors. And then as I see something of interest, I can steer the system. So maybe I'm interested, sorry if this is hard to read, IMDb ratings. And then I can see some descriptive stats, and then I click it, and then it changes the input to a recommendation engine. So now I see summaries, particularly of that field, exactly what I asked for, but then I can take one step further in my search. So now I'm saying, what are all the interesting combinations of IMDb rating with other fields? So I'm actually populating a gallery. And again, these ideas of searching over a language, generating a set of useful representations, ranking them, clustering them, et cetera, is actually going on behind the scenes. So in this case, we're using Vega Lite, a high-level visualization language, as the DSL for exploration. And of course, you continue this process and get more and more specific. So in this case, I've actually gone down and now looking at the combination of IMDb and Rotten Tomatoes ratings. In this case, I see suggestions about subdivision by creative type. So do I see different relationships, for example, in the average ratings based on genre information? And of course, for any one of these sets of data variables that we're searching over, there may actually be a large space of visualizations. So what we've done here is actually cluster all the visualizations and then try and pick the best one, where best is defined by both a combination of perceptual principles and sort of how well it fits into this gallery. So I might be interested in this thing involving creative type here on the left. So I can ask for, well, show me the rest of the visualizations that got suppressed in this particular case. And so I showed a subdivision by color initially, but a really powerful technique, but one that is less space efficient, would be to show small multiples instead. So I actually go in and browse the different variations of the visual encodings, whereas at the top level, I'm really exploring the variation in data variables instead. So again, it's really trying to also support this sort of ambiguity of intent, as I'm trying to get a bearing over a large data set, but I can also steer the types of recommendations I'm getting to aid that initial exploration. So that's just one example. There's some others in the space that we're exploring. I won't walk through all of these, but this is a great cheat sheet if you want to ask me any questions after the talk. These are all some of the issues that come up. So there's been lots of work certainly in processing ambiguity of input, such as in speech or gesture, where you assume there's an unambiguous intent and you're just trying to figure out what that is given a noisy sensor. And I think there's a different approach here that we're still hashing out, which is, what if the user has a vague notion of what they want to do? How do we support how they proceed, which is very common in more exploratory tasks. There's obviously issues in terms of what problem domains are a good fit for this approach. We've also explored in other work mixed initiative approaches. So what if the system automatically starts making suggestions in addition to responding to user input? And there's some very unintuitive results in terms of how do people react to those systems. So it's a rich area. And of course, many other issues. What if the programs you generate are non-deterministic? How do you know they did the right thing? And of course, there's the question of how do we engineer these types of systems? And on that last point, I think there's an interesting research area in terms of how would you start to systematize some of these ideas into a UI toolkit? One, to make them easier to build and to explore that space, but I think it also raises individual questions that are interesting in their own right. So one is, how do we design these domain-specific languages? If we can get some assumptions on their structure, whether it's a chain of operations or other types of language structures for modeling the task, can we build tools that allow designers to translate their knowledge of what people want to do into prototype designs of this language? I think this is very analogous to information architecture and website design, where you think about the data model and the layout, but now you're really trying to do this at the task-based level. So can you get designers who have that understanding involved in this loop earlier, maybe even have more power in the design process, because they can set up the scaffold in an application that's not so dependent on developers. So I think that's one interesting question. And even if this was only a prototyping tool, that may have some great value for the process. The other is, once I have this scaffolding, I can do a lot of interesting work in interface synthesis. So if I have a good model of the language and the parameter types, automatically generating a menu-based UI is pretty trivial. It's not hard to do. Now, and you might do other things, like be able to do some of the orchestration of the application relatively automatically, including history management, undo, redo, et cetera. And then you might have them plugins that for people who want to build custom content representations with certain affordances that really scope some of the development effort. You can plug these new components in. And for maybe common data types, some of these would be provided automatically. So there's a bit of both an interesting toolkit question here, and how much can you maybe automate some of these design issues, particularly useful for retargeting if I want this to run on the phone as well as on, like, say, a desktop web browser. And finally, another related issue that I think is really interesting and that we're actively exploring at Trifecta is, how do we use this in the context of interfaces that learn over time? So one is, like, if we have some assumptions on the language structure, we might also be able to provide a standard set of inference procedures for improving search and ranking over time. And I think, related to the earlier point, synthesizing the instrumentation to enable this learning over time can be incredibly valuable. So one of the problems is, like, you have a classification or prediction engine, it's generating predictions, that's populating a drop-down or like an n-best list, and then anytime a user makes a selection, you need to know not just what they selected, but what were the other options. And you want all of that data tagged and archived so that you can do learning, whether it's on the fly or in batch form, as you collect this data over time. This, even just by itself, without any of these other things, could be incredibly useful for studying how people are using your application within the context of this task model. And then finally, as our interfaces maybe adapt, understanding the ways in which they're adapting is really important as well. So especially if I'm going to do that for personalization, or maybe in Trifecta for us, like maybe customers in oil and gas and customers in finance actually have really different patterns, and we want to learn different models. We want to be able to inspect and understand those differences. And so as we think about trying to operationalize these predictive interaction ideas, I think it gives rise to a number of things that would be very interesting to explore on their own, but I think also kind of cohere together in this larger vision. And so this is something I'm interested in doing, but I also think it's something for other people to do. So if I don't get to it, please pick it up and share with me whatever you happen to learn. So just to review, what I've talked about today is sort of a speculative, but I think we have a couple points in the space that prove might be interesting approach to how to do predictive interaction over much more complex domains. In this case, by really modeling the task using a language, which we then use as a formal object for both reasoning about user tasks and decoupling that from runtime things to allow repetition, scale, et cetera. So with that, I will wrap up, and I'm happy to take any questions you might have. So thank you.
So you partly answered the question.
Okay.
I was wondering about graceful degradation of your tool.
Yeah.
So, I mean, the insights that you can get out of it really depend on the fact that the data has to be clean and in a certain format. And of course, you have tools to clean up the data as well. But even if there's something, for example, for the John example, if you have something where a field where a person does not have a first name missing,
Yeah.
or it's in another language altogether, how does your tool perform?
Yeah, so there's a couple places, under the bullet of performance cliffs. So one thing is, what if I'm trying to do something and the predictive interaction system just can't predict it? So some of the things that we've looked at is, like, a lot of times you have predictions that are very close to what the user wants to do, and they can see that. So some of the things we're exploring is, like, what are the mediation UIs that then allow you to, without writing code necessarily, still allow you to manipulate language structures, maybe in a more modal kind of dialogue-based thing, to actually make those transitions. So that's one issue where that comes up. Another one, which I think is related to the point you're raising, is sometimes errors occur. And how do I do that? Sometimes I don't even know that they're occurring. Not only does it happen like right away, and I might try and mediate it, I might be working with a sample of a large data set, generating a program, I set it off and I run it, and then it encounters data that's unlike any of the kind I've seen before. And so there's actually this outer loop to that guide decide process. And so what I didn't show you here is that in Trifecta, when I'm comfortable, I can hit run job, and like, depending on what your computational engine is, whether it's on your local desktop or on like your Hadoop cluster, you set that program, you set it running. Not only do we run the program, but we profile the results. So you actually come back to a page that says, here's the summary of your job run, and here's all the new type mismatches or outliers, et cetera. And those actually allow you to pull new samples. So I can actually pull in new samples into the system that consist of anomalous data, and then try and iterate on that. And so there's both this sort of inner loop iteration and outer loop iteration that I think you have to support in order to make this work beyond the immediate data that you happen to be looking at. Yeah.
That compute job sounds a lot like compiling a program.
It's exactly what it is. That is 100% what it is. And the fact that we have this sort of interesting thing where the program, the DSL for expressing the user task, becomes the major decoupling element. So the UI can reason in terms of that language and apply it on local data, but then I can just take the resulting program and then hand it off to compiler that then decides, based on where I'm running this, how can I optimize that compilation, whether it's to generate a Spark program or to just turn it into the best JavaScript I can to run it in my browser in Node.js, et cetera. So there's a nice decoupling too, where you can actually take some of the user design aspects and some of the more core computer science aspect and create some very clean interfaces between them. Yeah. I know I had David had lots of questions earlier. You have to tell me if I answered them successfully or not. Cool. Yes, sir.
I was wondering if work on formal ontologies had any bearing on what you do, or is that too general?
So yes, it did, in the sense that so far as we could avoid complicated formal ontologies, we were happy to do so. And the fact that if it became semantic web complete, we knew we would have failed. But it does play a role. So one place where this comes up right away is in data types. So I can look at a column of data and I can try and infer its type. And that can be low level, like these are numbers, right? Or even with a certain precision, right? Or I could say, these, based on the distribution, this looks like currencies or something else. And so there's these semantic roles, these higher level types. And these are incredibly powerful because once you know that, there are data cleaning procedures or standardization procedures that are specific to that type. So we do a lot of inference for things that are very common, obviously like state names, zip codes, phone numbers, credit cards, you name it. And then we have specialized suggestions that are unique to those types. However, we have to kind of constrain that because we don't want to go whole hog either. So there's a fair amount of type inference, and I didn't touch on that much, but that's another place where we do a lot of learning. But we also try and focus that. And in the future, as it gets more complex, we may actually want to limit it in terms of type packs that are more specific for different types of data. Because we don't want to get into the all-encompassing ontology game. Useful shallow ontologies, fantastic, but we are not trying to do some sort of grand old-school AI modeling challenge. Yeah. Yeah, sorry, in the back, and then Scott.
So I'm just curious, from your perspective, how do you think, what are some trends we should be paying attention to in terms of the impact of visualization on the sciences, say particularly the social sciences?
So I'm the type of person, I like big, grandiose ideas, but I often find that the more interesting stuff is in the nitty-gritty details that people consider beneath them. That's why I got into data cleaning, because I'm like, crap, I'm spending all my time doing this, and why isn't people, talking about it? In stats and databases they have, but then I saw, I think there's a beautiful HCI problem here. And so similarly, I think the number one thing that I see as an issue in the sciences writ large is the presumption that visualization is a communication tool. And it absolutely is, but that's not all that it is. So a lot of people are like, oh, I want this great figure for my paper, or I want to do something that's shiny so it hits the cover of Science. I don't really have qualms with that, but I do think it's underselling the value of visualization. And so to get back to that nitty-gritty, I think the number one thing that I think is useful in almost any analysis I've been in is visualize the data first in a way where I'm not trying to answer, fancy hypotheses. I'm trying to just understand, do I trust this data? What assumptions can I make of it? It gives me new insight into the process that generated that data. What are the gaps? What are the errors? Because there's always something that's not what you expect. And that's the first line in a richer exploratory analysis view. And then going forward, there's more sophisticated things that I think are really interesting in terms of how do you use visualization for exploratory analysis But think about it in a way that I don't fall prey to certain statistical pitfalls. Like if I'm looking, if I have small number of samples, I might have high variation. And so then ranking things from highest to lowest, the highest and lowest are usually meaningless because they were small sample. So I'm only looking at the averages, that I'm going to be totally misled. So I think there's some ways tools might safeguard against some of that. The other is people who test on their training data. And that's a huge problem for machine learning, and I think also for statistical analysis. Better support in the sense that I'm going to use this data to help refine, test, generate hypotheses. I don't want to then run like my ANOVA on that same data set because there's actually my p-values. I have problems with p-values in general, but more generally, those p-values will be wrong because they don't take into account the exposure. I think the larger crisis is actually moving away from that to more inferential methods. I think confidence intervals and particularly Bayesian credible intervals are much better ways of thinking about data, and there's a sort of a slow revolution occurring there. Nonetheless, you don't want to kind of make your grand claims based on the data that you use to figure out what the model should be as well. Yeah. Thanks. And then Scott, you had a question.
So you started out with Clippy, and I mean I think that any interface designer who sees Clippy is both like, that was a bad idea, but also you could see the impulse for why somebody would have wanted to go that direction.
Yeah.
And I'm kind of curious about two related things. I mean, one of them was that one of them is a research problem sent question, which is that you realized in this work that there was likely gold to be found in the direction that you went.
Yeah.
And I'm curious how you saw the potential for predictive interaction when the prior stuff had crashed.
So I think you have a second question, but let me just go ahead and answer that one. So a short anecdote I left out is that when we approached this, we were certainly interested in it from a language standpoint, but maybe one that's actually more akin to Tableau. Was like, is there a set of operators, and could I come up with a nice interactive set of gestures or actions that express all of those things? The problem we ran into is ambiguity. Like when I select text, well, that seems like a very natural and necessary thing to do, and it could mean one of 5 things. And then the interesting point was that which of those 5 is often, not always, but often predictable from other contexts, including the data itself or the type of text you selected. And the other, and the really critical point for us was that it's about 5 things and not 500. And that was the major insight, that there was a sparsity in the thing that would allow prediction to be successful. Where we're like Clippy, it's like, okay, I'm only going to write so many letters in my life, and how does that really help me? But the fact that the thing that I think was part of the set was the set of operations that we identified, which actually came out of a long set of research in the database literature, including a bunch of prior work that Joe Hallerstein had done at Berkeley, showed that this was a good expressive set, but it wasn't immediately always what people thought of. Like, I want to make the table do that reshapey thing where it goes from here to here. And that might actually be a set of like 2 or 3 operations. And so even then, thinking about that intent, but their inability to actually express it, can they actually interact with things that will help them find the right way? Later on, it was a big boon to us. And the final thing was that as we did that, the realization that previewing the action as opposed to just giving the thing, really closed the loop in a way that was a huge accelerator and made it accessible to a much larger user base. So we didn't come to it by grand design, we came to it by necessity, and then just in this case really benefited from the problem domain itself. So I think the interesting question from a future research standpoint is, do we have analogous structure or sparsity in other domains that we can take advantage of? And that may come actually through task subdivision, like by knowing that you're in a certain mode or you're trying to do a certain subtask, that will change the priors in the set of language elements that you search over, or that's just, it's not such a huge space that we can actually do well. And so I think that's something we'll have to contend with as we figure out, does this work well in other areas? And you have a second question.
If nobody else has a question, I'm curious. So given the insights that you had from your work here, how would you redesign Clippy?
So my first thing I say is if I removed the paperclip entirely. So the other, I go back to Eric Horvitz, Bayesian network model, which actually learned over time, which I don't think Clippy ever did. And now with the web and the rise of the internet, it'd probably be easier for someone to do that than it was back then. And then see about what are the types of actions that it's doing, and how do you surface those in maybe less interruptive ways. So in the case of spell check and grammar, it's usually pretty easy for me to turn them off. Every once in a while it's annoying, but for the most part, those little squiggly underlines work pretty well without being too intrusive. And I would look for similar things, like are there areas or real estate of the user interface where I can surface some of these things in ways that might also be contextual, like we'll only show that when I'm actually interacting with that paragraph, for example. So that's the first step I would do is A, make sure that my model is smarter if I could, and then 2, think about ways that would actually give a much more kind of blended interaction mode that sort of kind of comes out of the seams in non-intrusive ways in the UI Chrome as opposed to jumping up in my face. That said, I do know people who loved, not Clippy, but they loved it for totally different reasons. Like I knew people who would like turn to the cat avatar and leave it on because they loved cats. And they said, the best thing about this cat would be is if it never suggested anything, but just stayed cute in the corner. And I think that's also interesting, but I think that's on a totally different tangent. Great. Well, thank you very much.
Thank you.